All right, it is 7 o'clock on the West Coast, and we are live with 5Live Free Code School. This is our first actual class where we get into instruction. We did introductions a couple days ago, and that was great. But if you're going to tune in or you're watching this at some later date, this is where the curriculum actually starts. And just to refresh anybody, remember, anybody who's watching, my name is Eric Gross. I'm teaching Free Code School. I have 5 students inside the actual virtual classroom in this Zoom meeting, and anyone else is free to follow along, learn, do homework, and become well-rounded entry-level full-stack developers like these awesome people are learning to do. So let me pull down the little logo, pull up the Zoom call, and say hi to everyone. Hi, Jason. Can't hear you.
I guess it would help if unmuted.
Yeah.
Yeah, sorry about that. Yeah, for some reason I thought Mondays were 8 p.m. your time.
Well, that actually brings up a question that I had asked the other folks earlier. Would it be fine if all the classes started just at 8 o'clock Pacific?
Oh, yeah, that would be fine with me.
Good. All right, I'll adjust everything. So it'll be a little more consistent, easy to remember, won't be a big deal. All right, so here's what we're going to go over today is some of the fundamentals of computers and technology. And along the way, I'll be asking you guys for your thoughts and ideas on a lot of these things. We'll be clearing up, the precise meaning of certain terms. And especially during these first few sessions, I really want you to totally be willing to interrupt me if there's a thing you've always wondered about and what we're talking about sparks that interest. Don't let that fleeting thought go away. Cut right in and go, hey, Eric, we don't need to answer it right now, but I just thought about blah. What is that? And we'll note it down and we'll make sure we don't skip anything, because these first few sessions are really about laying down the foundation of the technical terminology and concepts underneath technology. And I've just found that the more secure and certain you are of the meanings of these words and what they represent in the physical universe, the easier it is to navigate much more complex layers of this whole technology landscape we're learning. So we're going to lay in fundamentals. So please interrupt me at any time. All right, off on the other side of this second monitor here, I'm going to pull up some notes we have on curriculum. All of this will actually be put online afterwards, so you can refer back to it and refresh your memory. And of course, there's the recordings that you can watch. So here's a question, and when I ask these things, I am absolutely not looking for a right or wrong. I just want your thoughts, and we'll kind of refine it as we go. Can someone just take a crack at explaining, like, what's a machine?
So a machine is something that it kind of performs some kind of operation to make like things easier.
That's really good. It's really good. Actually, that was actually really good, because it opens up a part of it I really want to explore, which is that with certain rare exceptions, I don't know if mankind has ever made a machine that didn't in some way aid mankind's survival. Sometimes that's a very legitimate, it's a life or death thing, or it's a great increase to civilization, or sometimes it's super silly. When I start looking at this, and that was a great definition, Alexander. When I look at this, what I think of is like a machine that really, if you look at history, makes people go, oh, well, yeah, that would make a huge difference. Is back around 2,500 years or so ago, a fellow named Archimedes in Greece, and he had a screw that he invented. And they were usually about 5 to 15 feet long, made out of metal or wood. And they were a spiral with a central shaft. And what they were used for is just to raise water from one lower elevation to a higher elevation. And with that one little invention and some way to wind it and move water up between 3 and 10 feet, he changed civilization across a broad swath of the Mediterranean and Southern Europe. That one little thing. And that's a machine. A machine is, like Alexander says, some kind of a tool or device designed to help, to fix a problem. You can further expand it and say, well, they generally have some fixed parts, some moving parts. But that's really a great description, Alexandra. Any questions or comments on that definition of machine? Is that acceptable? Does that make sense to folks? Okay, so let's look at another word that is pretty common in this industry. And again, we're laying down fundamentals. Some of these words you can be like, Eric, I've known what that is since I was 12. There's a method to the madness. What does compute mean? To compute, the verb.
To calculate.
Good, to calculate, absolutely. Any other thoughts, definitions to the word compute?
Change.
Say it again.
Change.
To change. Tell me about that. What do you mean by that?
It's a change the form of anything that I didn't know, deducting.
Okay, so addition,
multiply.
subtraction, that sort of thing.
Yeah.
Okay, good. Absolutely, we're right in on that area. We don't need to quote the exact strict definition on this, and that's not my intention. There are many dictionaries, and you can look it up. Here's the aspect of it that I'm going to ask you to consider is meanings like to determine the answer to something, figuring out a problem using numbers. These are all compute, right? To evaluate something with the purpose of coming to a conclusion. How many of you are aware that the word computer actually referred to people before it referred to machines? Anybody ever heard that before?
Read it in your book.
Yeah. Do you remember what it was in reference to, Jason?
Yeah, just some of the very first mathematicians, like people were just called computers. They would do math using like abacus or something like that, maybe.
Absolutely. Absolutely. And in the early days of the space program, before they really were able to get computers up to the state where they could be a significant aid and they could be trusted, they brought in huge banks of people who were very skilled and precise and did make a lot of errors to do math. And those were computers. That was their title. Most of those workers were female. And as these digital machines came into being, these actual computers as we know them, the methodology used by these people that were called computers translated over pretty directly. And many females, many women moved into this emerging computer industry. And the fact is that, and this is something that I'm very passionate about, women formed the backbone and initial thought process of much of the computer industry. But that's part of how it came about. Is computer was actually a job title because they figured out a problem using numbers. They determined the answer to something. They evaluated something with the purpose of coming to a conclusion. That's what compute means. You all gave perfectly fine definitions for it. I want to separate out the idea of compute from the word computer, because we always think of that as a physical machine, these electronic devices. Just means to solve a problem, that's all. Any questions on that? Any comments? Okay, cool. So now let's look at what is a computer. Anybody have a decent definition for a computer?
Maybe something kind of similar to like compute machine where it takes in information and then also changes it and then gives something back.
If I could high five you through the computer, I would. Like, you have no idea how happy that made me. Because what you also express is the purpose of a computer. One, you're 100% right. It's a machine that computes. But you really looked at the nuance of the purpose of a computer, which is to take in information, to work with that information in some way, and to send information on. As complex as these things can be, that's actually all they do. And if you start from that simple, almost sounds stupid, but it isn't, definition of what a computer is and what its purpose is, now you're on the right track. It's just a machine. It takes in data. It transforms or works with the data in some manner, and it sends that data on to either another computer or to some other device. That's all it does. That was excellent. Okay, so let's dive in a little bit more. Have any of you ever had this question about whether or not computers can think? Either heard it posed or wondered yourself if computers can think?
Well, it's kind of all over the movies. Yeah, I guess it's one of the fantasy that we have as human beings.
Yeah, it is. Both in literature about the modern age and about the future and science fiction and all that kind of stuff, right? As technology exists right now in this world, do you think the computers can think?
No.
You're totally
They're
right.
just doing what we are telling them to do, I guess.
That's exactly it. They're simply doing what we tell them to do. And when you look at very simple operations that a computer can do, that becomes pretty clear and it's inarguable. What makes this area a little bit fuzzy for people and makes some people actually kind of think that a computer can think is just the sheer complexity of the kinds of sets of instructions you can put in a computer and how fast they can do them. And two, this is the part where it gets a little weird, is on the surface, to someone who doesn't know what's underneath the hood in a computer, the actions of a very, very complex computer program, and especially a computer program that utilizes the work of hundreds or thousands or even hundreds of thousands of computers all at once, the actions of that kind of a system can appear to be self-originated. It can look from the outside like somehow that system or collection of computers spontaneously, based on something that we can't understand, came up with a thing, brought it into being. It can really look like that. And as we increase our knowledge of the different architecture you can have in networked computers and all that kind of stuff, you'll gain a little even more understanding of how to set those things up that have that appearance. On the outside, it looks like, wow, that system came up with that. There's no way a human being could have come up with that. That computer program did. We're only in that stage, because of the massive number of computers we can all harness at one time to work on things. But if you follow it all the way down, each one of those individual computers is only ever doing something that, as Ellen said, we told them to do. And it's a pretty important thing. As you move into the technology industry, you're going to find more and more people look to you for resolving some of these confusions they've had about technology. And so I like to knock that one out right at the beginning. With the current state of technology and what these computers are, they can't think. They can only do what you tell them to do, even though it might look different on the outside. Any questions or comments about that? Okay, cool. All right, so let's talk about a few more things. I want to look at just the concept of a language, never mind programming languages. Can someone give some sort of a working definition for what is a language?
A mean of communication between two individuals.
Good, excellent. What does it make use of? What are the parts that kind of, you say the means, and that was a great explanation. What are the things we make use of to do that?
You mean what's happening when two people?
No. Although that is a really interesting thing. We'll talk about that later on when we talk about how computers talk to each other. But especially written language. What do we use to make that occur? You said like a way or means to.
Well, we need a convention that we all agree upon, that we all agreed. Otherwise, I mean, if you decide your own language and I read, I won't know what you're trying to.
One, that's funny. Two, there's a whole movie about that. And three, you just brought into the conversation one of the absolute most important things about computers, the convention part. We're going to come back to that over and over again. So that was pretty cool. But yeah, when we're talking about human beings, there's got to be an agreed upon sort of way of doing this. When it comes to the written languages, what are the things we're writing down?
I'm not sure.
Feelings.
Say again, Sudesh?
Feelings.
Okay, not the thoughts we're expressing, but literally what are you writing on the page? What are those things called?
Letters and
letters?
numbers.
Letters, which
Yeah.
put together make up words. Good. And we also use symbols. It's not really words, but they're symbols. There's no trick on this at all. I just want to break it down to like the simplicity that we hardly ever think about because we all learn how to read and write. We know how to communicate. But when you're writing in a language, you're using words and symbols. And yes, they communicate, as Ellen was talking about, right? What is a computer language or a programming language? How is that the same? How is it different? Any thoughts on that?
They both have like that agreed upon way of communicating, like the rules, like Ellen was saying, and then also like syntax and grammar to it.
Good. Yeah, you're right. There's that agreed upon way of thinking. But there's an important distinction that I want to just have you guys place your attention on. When you're dealing with human beings, you have that, we're going to call it a protocol, Ellen. Just, you talk about that convention or that agreed upon sort of system, because we're going to come back to that word protocol a million times in computers, right? But we all agree, for example, on, at least in the English language, the letters that make up the alphabet and the rules of syntax and spelling and grammar and that sort of thing, right? We agree upon these things. But in that language, it's pretty easy to play fast and loose with those rules or those conventions and still accomplish communication. Here's an example, and one that when I was more of a jerk when I was younger, I would really get upset about. You're driving down the road and you see a convenience store and it's called the Easy Stop. The letter E, the letter Z, and the word stop. Easy Stop. We all know what it means. It's not actually saying the word easy, but we all know what it means. We can intuit, we can extrapolate, we can figure out what was intended. We might be upset about it, like I used to be, because I was a jerk. But you see what I mean? We can make connections there. The languages used by computers are incapable of such things, unless a human being thought ahead and said, oh, well, there's this pattern, EASY. I've told the computer what that means. But then I input EZ because it seemed faster and I kind of knew what it meant. And the computer went, doesn't compute. I can't understand it. We're going to come up against that over and over and over again. And really, honestly, this comes back to what Ellen was talking about, which is no one told the computer that that was a rule. No one told the computer that was a permissible arrangement of these letters and symbols. And because no one thought of it ahead of time, the computer literally doesn't know what to do with it. Now, I know I'm beating on this part pretty hard, the idea that a computer can only do what human beings have told it to do. But we're going to come around in a few minutes to the actual exact physical device inside the computer that makes everything we're talking about here true. Makes it true that, yes, as Alexandra was talking about, there's an exact defined syntax, rules to this language. But also makes it true that, like Ellen was referring to, if there's no convention or protocol, or if something comes in that doesn't match that convention or protocol, that a computer literally cannot work with it. We're going to look at the exact physical device. Now, most of us who've worked with computers kind of know that's true. Like you give it an instruction and it's not a properly formatted instruction, we know that it's not going to work. But there's all these things that come up where you're like, well, I know what the rule is. I'll give you an example. Have any of you here ever made even a very simplistic web page? Like you've written down some HTML, right? Now, there's an exact specification for HTML. And we're going to learn a lot of details, but here's a simple thing, which is that you've got some content, usually text, and on either side, bookending it, is an opening tag and a closing tag. It might be like a P or paragraph tag at the beginning and the end. Simple enough. We've all written little things like that, right? We all know the rule that if you have an opening tag, you've got to have a corresponding ending, closing tag. That's the rule. But the fact is that those documents that would write like that, they're being fed into a browser like Chrome or Internet Explorer or Edge or whatever, right? And they're the ones that are responsible, frankly, for caring whether those rules are met or not. That browser and the programmers that made it have a choice to make. They can look through that document that came in and see the opening tag and then the content and try to find the closing tag. And if they don't find it, they can throw an error or mess up the display. Or if the programmers who made the browser go, you know what? We understand programmers well enough, and we understand and can find out what comes next, what opening tag is next. We know that they just missed this one. So we'll act as if it's there. They're very liberal in their interpretation of the convention, as Ellen was saying. And so if you as a programmer, especially if you're learning at the very beginning and you're following some tutorial and it's saying you have to have an opening tag and then the content and a closing tag and so on and so forth, and you're writing it, and each time you make the change, it's fun. You're making the change, you write the code, and then you pull it up in the browser, and you write the code, and you pull it up in the browser. Those first few, like that's the first experience for a lot of people who end up being software developers, right? And you've read the rules, and you forgot a closing tag. And you're like, oh, that will mess it up. And it doesn't mess it up in the browser. Your certainty about what Alexandra is talking about starts to waver. Wait a minute. I was told I have to format it this way, that it wouldn't work without it, but it worked. Do you see how it can be a little bit destabilizing? But ultimately, it only behaves that way because a programmer told it to. They just don't know that. So here's where all this is leading. We're about to look at this physical machine. We've cleared up what a machine is. We're about to look at this physical machine called a computer. We know the purpose of one, to take in data, work with it in some way, and send it on. We're now going to take all that in this abstract, well, those are great words, and look at the physical machine that does this and start diving deep. Now, for some of you, this is going to be stuff you kind of already knew. Jason, in particular, I'm thinking of you. You've built computers before, right?
Yeah.
Right. Have any of you ever also put together a personal computer before?
No.
Okay,
No.
good. Okay. This will be new for you. And it might be along the way. Jason, do you pick up some new stuff?
Oh, absolutely.
Good.
Yeah, you can. It's definitely definitely something I like to go through.
Good. Which brings me actually to a point that I didn't make last session when we were talking about, how the class is taught. For almost every single thing that we learn over the next however long, it's inevitable that you will come across something that you actually already understood pretty well. It's just going to happen, right? When that happens, there's a specific thing I'm going to ask you to do, and I can only ask. If we're going through something and you legitimately are like, wow, that's exactly the way I thought it was, and I kind of already knew this, The thing I'm going to ask you to look at is if you can now view that data, not as learning it for the first time, but if I were going to try to simplify this for someone who was a novice to the subject, how can I explain it to them? Is any of the data that Eric's going over useful to me to further inform my ability to speak to non-technical audiences? Because while we haven't covered it much, one of the key things you can do to ensure a successful career in technology is to get very skilled at how to interact with technology adjacent people. You're going to work with tons of them. And life is very, very hard for them if they're dependent upon working with technology professionals, and yet they're lacking the fundamental understanding that you already have and are learning. It's very hard for them. When you get past the social veneer, and I've been able to quite often, and ask them what it's like, they're lost. And they have this imposter syndrome that's insane. And they've got mysteries about different words and what they mean. And they've got to act like they know what they're talking about in front of hiring managers or whatever. And it's miserable for them. If you're able to bridge that gap for them in simple ways that they can understand, you are just miles above many developers. It's a real big deal. So if we encounter things you already know, well done. Look at it from that point of view. Is that cool? Okay, so now let's get into what's inside these computers, the actual physical machine and how they work. I'm going to start diagramming some stuff out. So let me get that thing set up with my my iPad. I think I found a better sketching app. We'll see how this works. Awesome. Okay. Actually, let me show you one other thing first before we draw this diagram out. This is an old computer, probably 15, 20 years old. Doesn't matter. All the concepts apply. Everything you're seeing on here, the fundamentals of have been true since about 1977.
Could you share my screen, please?
No, you have to, what I want you to do is just concentrate really hard on my mind. I'm kidding. Sorry, hold on a second. I don't want you to concentrate on my mind. I feel sorry for anybody who does. Okay, so this picture is clearly of an older computer, probably 15, 20 years old, but the fundamentals inside here apply. Now I'm going to lead you through this in a very specific order, and it has to do with like the physical nature of it. And along the way, this part's super important. If I use a term you don't understand or want some expansion on, let me know. We're going to begin in the upper left here. Sorry, at the bottom left here, at this box called the power supply. Now, Jason, I want you to answer last. I'm only going to call on you if I need to, okay? Can anyone tell me what they think this power supply does inside a computer? Right answer, wrong answer, I don't care. I'm just curious.
Supply the power to the computer.
Good. So here's my question. Why does there need to be a whole big box in there? Isn't power coming in from the wall on a cord? Why don't we just connect the wire into the places that need it? What's that big box going to do?
It's control the power for components to match their power.
To match their what?
Voltage.
Good.
Current.
Yeah. Okay. We're getting into the exact right area. Okay. Anybody else? Again, besides Jason yet? Anybody else have any like thoughts on what this metal box there called a power supply and all the things inside it might do? Okay. So let's look at this for a moment. Let's try the sketchy sketch. Can you guys see my iPad?
Yeah.
Okay, good. All right. So how many of you have studied some basics of electricity?
I did.
Good. A few of you. Okay, good. All right. So right now, we're just going to consider. Let's see. I don't want black. Right. I want black. Okay. We're just going to look at this computer as a black box. We're not looking yet at what's inside it. And we already know that it's a machine, which means it's got some solid parts. It's got some moving parts. And we know it helps. I really loved that was the first thing you said, Alexandra. That was great. So it needs some energy source. And again, some of the stuff is going to be so dead simple. Like, Eric, why are you going over this? I want you to be able to explain these things to people that are completely non-technical. And at its core, I really want you to understand the computers are really stupid simple. They're very simple machines. So we have energy that comes in. Now, it comes in obviously in the form of electricity. Electricity, as you probably know, has a different sort of like level of what we're going to call potential energy. How much work is it possible to do? That's a question mark right there. How much work can it do? We measure that in this thing called volts. Oh, wow. I'm telling you, spelling is so important in life. Volts. So let's erase all this stuff here and just say this energy that comes in from the wall, how many volts is it in America?
120.
Yes, 120 volts. How much is it in the UK, Sudesh?
It's 240.
It's 240 volts.
Yeah.
Why you got to brag? Why you got to brag? Is the UK so impressive? They have double the voltage that we do. Is that what you're saying? Okay, good. I think that's awesome. All right. Regardless of whether it's 120 or 240, here's a thing to understand. Now, I've said that this big black box, we're not going to look at what's inside it, except to say that it has lots and lots of tiny wires. And here's a thing to know. If you have a wire, you have one end of it, and it goes to the other end. When electricity is going through it, what it actually means is that electrons are moving along the wire. It's actually kind of wild. Why is this not drawing? What did I do? So electrons are actually moving. And as they move, what do they do to the wire? Any thoughts?
Eat.
Absolutely. Heat goes up. And again, this is some basic science. It explains some key things of fundamentals. So if electricity Here's electricity moving through the system, moving through the wires, and they get hot. Well, what affects how hot they get? What are your thoughts?
Would it be how much electricity is moving through it? Is how hot it's getting?
Exactly. If we go back over here, it's how much, oh, that's a, how many volts? Because remember, volts are potential energy. Potential meaning they're not going to do anything until they're allowed to travel. Until it's allowed to travel through a wire, it's not doing anything. Hey. So if you have more volts, you get more heat. It's that simple.
So does that mean that computers in Europe are better to resist heat?
That is actually an incredibly insightful question. The answer is no. And that, Ellen, is why we have a power supply. That was actually a really good question. The fact is that if you look over here at these wires, right over here, we have this wire. They are very small. If you were to try to put even 120 volts through these wires, they would literally burn up. The heat gets so much, it would melt them and they'd be toast. 240, don't even think about it. So the voltage coming in from the wall, we can't use it. We have to lower it so that the heat doesn't get too high. You follow? That's one of the key things a power supply does, is it lowers the voltage. How far down does it lower it? Any thoughts, any ideas? Anybody know? You're allowed to answer, Jason, if you know.
I really
Yes.
don't know.
No problem.
Just enough. Is it the demand?
Nope.
From the,
It's a constant level. It's 5 volts. This is true of almost every computer made in the world. No matter what comes in, whether it's at 240 because you're in the UK and other countries, or whether it's 120 in many other countries, regardless, the power supply will drop it down to 5 volts. Now we're going to talk about why 5 volts in a moment. We're going to expand on this whole thing about 5 volts. But let's talk about one big giant side effect. This thing called a power supply, technically, it is a category of machine called, oh, that is not what I wanted to do. I'm still getting used to this one. It's called a transformer. Has anybody ever heard of transformers before?
The movie, yes.
Anybody ever heard of transformers like down the street on top of a pole for electric supply?
yeah.
It's the
Yeah.
exact same concept. I think I can do go back here and we can come back to this. Let's add one. If you have a telephone pole here, sorry, that's not what I wanted to do. You have a power pole. And you have another power pole right here. And then you have your house. Remember, this takes in either 120 or 240 volts. And what's coming along these wires right here and into your house is either 120 or 240. Usually it's 240. But let's look at a big giant city here This is a city grid of streets. And over here is the power station. The power station might put out 4,800 volts and send it from street to street until it hits a special little facility. And that is a transformer. And that will drop it down to 240. And that has to do with the fact that it's easier to transfer this electricity at higher voltages. There's a lot we can go into there. It's totally beyond the scope of what we're learning here. But I want you to be aware that this transformer thing is nothing new. We constantly need to go from a high level of electricity down to a low level for a lot of different reasons. And the machines in the middle, these transformers, when they do that operation of dropping from high to low, they produce tons of heat, a lot. We don't need to get into the science of why, although it's pretty nerdy and fun. They produce a lot of heat. This power supply right here, this is the main reason why your computer gets hot. It's one of the primary reasons why. There's some others. But just the very action of being able to drop from 120 volts down to 5 itself produces heat. So when you look at the back of a computer, and I think I can go like that. If you look at the back of a computer, right at the back of this power supply, you'll see a fan exiting outward. That's to pull all the excess heat out of that thing. Let me get that back of the computer image. And we'll open it up side by side. And if you look at that grating right there, that's airflow for a fan that's right inside. And it's right inside or next to the power supply because the power supply generates a lot of heat. I've literally known of people in the winter who put that thing really close to their feet because it keeps their feet warm, because it blows out hot air. All right. Questions so far? Again, interrupt me anytime you want to go into more detail or if I cover something you're not sure about. Okay. So far, we haven't even gotten into how a computer works. All we've talked about is the fact that because wires will burn up if we put too high a voltage in them, then we have to reduce that voltage with this power supply. And we reduce it to 5 volts. Now, why the exact amount of 5 volts? Never done the research, not that important. I will say this. It is easy to keep stable. We do not want the output of the power supply to vary. Remember, what comes in is from the wall. What comes out is the 5 volts. And for a couple of reasons we're going to go into, you do not want that voltage to vary inside the computer at all, really. You want it to stay pretty much exactly 5 volts. However, the voltage coming in the wall, how stable do you think that is? I mean, we said it was 120 volts or 240. Is that always very stable? Anybody have any insight into that?
No.
Was that no, you don't have any insight, or no, it's not always stable?
It's not stable. That's probably why we have trip switches.
We have what?
Trip switches.
Trip switches. Oh, yeah. Yeah, breakers, trip switches, something to interrupt the electricity, right?
Yeah.
Yeah. That typically is because it might spike high, right? Too much electricity.
Mm-hmm.
Yeah. Or it might drop low. Well, again, we're not going to have a big giant class on electrical distribution and all that kind of stuff. But let's face it, if we go back here to this other diagram, we can talk about this awesome power. What happened there? We talk about this power plant and just say, oh, well, there's a power plant. Well, that power is coming from somewhere. If you trace it all the way back, it might be that there's a dam right here. Here's the water level, and here's the water coming out. And right at the bottom here are a bunch of generators. And they're making electricity. This is electricity. How you like my lightning bolt? And the electricity travels and comes into the power station. Well, what if the water level drops? Therefore, the amount of pressure on the generator drops and the electricity drops a little bit. That could happen. Here in the American West, we're facing something kind of scary like that right in our own water system. If you haven't looked up Lake Powell, Powell, read it and be scared because the water level is getting lower and lower. But not only that, here's this power plant and it supplies a whole big giant area. Well, what if down in this area is the arena where people play football, proper football, Sudesh, with helmets and shoulder pads. So here's the arena. And all of a sudden they turn on every light in the arena. Well, that voltage of 4,800 that's being sent, it's going to drop a little bit, even if only for a few seconds or even a minute. Why? Because we're suddenly using up more of the available supply. And that has to go all the way back to where we get it from, and we start pulling more. It's not an instant recovery. So if the 4,800 drops, and we're dropping it down to 240 before it gets to your house, it's going to drop a little bit. And now our computer's in trouble because what came in dropped, which could mean the 5 volts dropped. And again, we're going to discuss exactly why, but that's a huge problem in a computer. So this is something, Sudesh, you were talking about earlier. Part of the job of this power supply right here is to keep the power coming out of it stable, right? Now, we don't need to get into how power supplies work. That's not the scope of this class. And frankly, it's not going to add anything to your knowledge of computers and being a developer. But you do need to know why it's so dang important to keep the voltage coming out stable. So now let's put a little wavy line here. And we're going to say that down inside here are all of the parts of the computer. We're not yet going to expand what each one is. But what we can say is the parts down inside here operate on a very simple basis. They operate on the basis of something is either on or it's off. Another way of looking at this, something is either true or it's false. Another way of looking at this, a number is either 1 or it's a 0. Now we're going to expand on exactly how that comes to be and why it's important. But that's the thing to know right now. Inside all of these parts that we're going to learn the important ones. This is the basis they operate off of. Right here. There's only 2 conditions possible in any of these devices. Yes or no, true or false, on or off, 1 or 0. How do we represent that in a physical machine? Here's how we represent it. All the ones on the top, let's make a little line here. All the ones on the top mean 5 volts is actually present. All the ones on the bottom mean 0 volts are present. It's that simple. In a computer, which deals with all of these decisions and operations and everything, the only way they can actually have any data inside them that means anything is a combination of, yes, there's voltage, no, there isn't voltage. And since the yes is supposed to be 5 volts, if we let that drop and it drops far enough, now it gets interpreted as a 0. And the entire basis for this kind of machine we created falls apart. Because now you don't know whether data is true or false, on or off, 1 or 0. And that's why it has to be so stable. Any questions about that?
I don't know if this question really makes sense because I'm trying to think of it in my head, but like if it has to be 5 volts to be like true, could it not be like anything that's not 0 is true? So like since the 5 has to be stable for it to be true, could they not make it just like between 0 and 5 is considered true?
Alexandra's a genius. Yes and no. Let's go down a little farther. And let's put down in here the question of, let's go to black. Question. Does it have to be 5 volts? No. But let's just start to logic this out for a second, Alexandra. And everybody else, I'd like you to follow along with this. Let's say we have at the top here 5 volts. And here we have 0 volts. And what I want you to do is I want you to start just slowly going up a little bit at a time. And you kind of just tell me, you don't even need to know electricity principles much to think with this. How much voltage do we need before we go, oh, we can call that a 5 reliably. We can call that a yes. We can call that a true. We can call that a 1. How far do we need to go before we know that that's what was intended?
Maybe anything that's above the 0, like when you get
About anything above 0, right?
yeah.
Okay, good. So let's talk about that for a moment. And again, you don't need to go super deep into how electronics work to understand this principle. If you have a wire, again, it connects from one point to another, point A to point B. And you're talking about, am I going to put 5 volts on there or not? That's what we're talking about. Is it's a metal wire. There's no magic to it. It's just a wire. Am I going to allow electricity onto it or not? Well, one of the things to know about these little wires is if they are near magnetic fields, that can actually generate a little teeny bit of voltage in them. Never mind how, although that's pretty weird, but it does happen. So now we instantly know that we need to figure out what that threshold is. What's the threshold where it's not magnetic fields? So we can't just say anything above 0. Now we got to go a little higher. There are other factors as well that we don't need to go into. The point is that there's a certain point where if it's below that, we know that there's no way it was intended that there be any voltage. There might be some, but we know that for the purpose of a machine that's supposed to differentiate between 5 volts and 0, that meant 0. If there's any voltage there, it wasn't intended and we can ignore it. And the same thing is true going up. Anything from a certain point up, we can go, well, it might be a little bit lower than 5, but we know that there's nothing that can account for it not being genuine. All the reasons it might have dropped have been factored in, and there's still enough. This machine is supposed to interpret that as a 5. Any questions about that concept before I give it a name? These voltages, and I think they're around like 0.6 volts and like 3.7. It's actually not important what they are. They are called threshold voltages. Because once you cross the threshold, you're in. Either going up, if you're at 3.7 or higher, call it 5 volts. That means yes, that means true, that means 1. Oh, we're below 0.6 volts? Call that no, call that false, call that a 0. Now, I don't actually expect you to remember all the details of this. And frankly, it's not that important that you do. The part I'm trying to reinforce is that inside a machine, a digital computer, oh, it's farther up, that all the parts in it, remember, we're talking about these parts right here, all of these parts operate on the basis that if they are being given 5 volts of electricity, and we now know that it's got a little bit of wiggle room, but it's supposed to be 5 volts. If they're given 5 volts, that is to be interpreted them as yes, on, true, 1, whatever the context needs, where it's forced to differentiate, we know it means the positive 1. And if it's below a certain level that we can reasonably just call it 0, that means that whatever part is meant to analyze that and determine its condition, you can call that a 0 or a false or an off. We'll get into when you would need to differentiate and what that would do to affect how the machine operates. But this fundamental, I want to make sure we don't go past. We started out bringing in from the wall here, highlight a little bit. We brought in electricity. Our power supply reduced it to 5 volts. We're now going to send it into these parts and periodically change it to be either all 5 volts or 0 volts. And that's how we control what the computer does. Either there's 5 volts there or there isn't. And that's how we can differentiate and start to build some logic. Any questions so far? Okay, cool. How many of you already knew this or some part of it? Okay, good. I want to take the mystery out of these machines. They're actually super, super simple. All right, let's put that up for a second. I'm going to switch over back to this diagram. We're in the power supply. Notice that coming out of the back of the power supply are a bunch of wires. And they go over to various things inside this box. All that is the 5 volts getting distributed all the way throughout the machine to be used as we need to. Let's look at one of the primary places it goes. It goes to this big green board called the motherboard. A motherboard is an example of what's called a printed circuit board. Can anybody explain what a circuit is? Any idea what circuit means? A circuit is just a combination of wire and devices that electricity can go through to do work. That's all. Look at the remote control that we all use to control our TVs. There's electricity in there. It's a battery. Electricity comes out one end of the battery, and it goes through a combination of wires and little devices doing work along the way. And then the electricity comes back to the other end of the battery. When we say a circuit, the word also means like a complete path. If you do a circuit around a racetrack, for example, you're going from the start line all the way around, coming back to the start line again. That's a circuit. It's the same word. And it means pretty much exactly the same thing in an electronic machine. Electricity comes in, goes through a bunch of wires and devices, and comes back to where it started. Any questions on that? Okay, so what that green board is, although they're very, very small, thousands of individual little teeny circuits. And they're sandwiched between these layers of green material. So a bunch of wires, a bunch of little teeny devices, and they all do work. Never mind what work they do or how. There's people that specialize in all that nerdy stuff. I used to work in that stuff in the Navy. You don't need to know it to be a programmer. You just need to know that that big green board has millions of little teeny electronic circuits in it, each of which does a little bit of work if you give them electricity. Now, on that board are most of the important parts of the computer. We're going to talk about the most important part. It's underneath this big blue thing, and it's called a processor. Anybody know what the other term for it is?
Would that be like CPU? Because that's how
Exactly.
I heard it. All right.
That's exactly what it is. It's the central processing unit. Now, that can sound all fancy, but it comes back actually to what you talk. And by the way, I'm turning to the right to look at you, Alexander, only because I moved the Zoom control. I know you're not over here. Here, there. So it comes back to what you talked about, Alexandra, which is like it helped us refine the purpose of the computer. The purpose is to take in data, to work with that data in some manner, and then send it on. The technical term for work with the data in some manner is to process the data. It's a very wide open thing. There's lots of things you can do with data, but that's what the computer is for. So when you look at the name of the most important part in that machine, it reflects the purpose. We're going to get data in, and we'll talk about how to get the data in. And we'll get data out of it. We'll talk about how to do that. But it's that piece, it's underneath the blue part. That's the most important piece. Now, let's see what they look like. There's a nice one right there. This is about, oh, look, there's in the hand. You see the size of it for scale? That's a central processing unit. They're about, I don't know, 2 inches by 2 inches typically. It's the brains of the outfit. When we say that the purpose, like we were talking about, of a computer is to take in data, to process it, and to send it on, this is where the data comes in, is right into this little physical device. This is the piece that does the processing, and it sends it on to wherever it needs to go. Other things that this CPU does, that it's all about. Give me just a moment. I want to pull up several things that are important to look at here. Okay. We're about to hit some of the time here. Okay. Anybody need a break? Okay, good. We're about to hit. Okay, this is all opinion from Eric. I'm doing this a while. There's a relative importance level to some of the data you can learn. Some of the stuff I went over tonight, for example, it's lower on the importance scale. How an electrical distribution network works in a city is extremely low importance. What we're about to cover is of extremely high importance. You have a picture here of a central processing unit, and we're saying, or I'm saying this is like the brains of it. This is what actually does the work. We're going to get into a little bit of detail of how that's done. We're not going to go super deep. There's a lot you could know, but we're going to talk about the parts that are enough for you to really be on solid footing. as a software developer. Let's go back here and look at a concept related to this central processing unit. Actually, I need to tell you how data gets into it. I apologize. Look at the back of this case, and I'm going to expand it a little bit. Or maybe I'm not. Will this enlarge? Please enlarge. Good. Okay. This may be old, but the concept's the same, and it'll be the same for a very, very, very long time. This is where the input-output devices will connect. Like right here is a mouse and a keyboard connector. Now, old school, they have a different form now. Who cares? They're still taking data in or putting data out, right? So the keyboard would be for taking in data. A mouse would be for taking in data. Here, right here, this DVI, digital video image or a digital video interface. This is for going to a monitor. So that's sending out data. This is high density media interchange, HDMI. That's for sending out data. These are USB, universal serial bus. They can send data in or send data out. This is the physical way that your central processing unit gets the data it needs. One cool thing is, if you look at this inside of a computer thing, and you see this, the motherboard, and right here is the actual processor under this blue thing. Right on the outside of the box is where all of those connectors are. They're right next to the CPU because all the data needs to come in and get to the CPU. So, any questions about that? All right, so let's look at this thing that Eric is going on and on about, which is, it's super important. Come on, you can start up again. I'm trying to mirror the iPad and sometimes it takes a minute. Did I lose someone for a second?
Yes, I don't know what happened, but I was gone.
Oh, I wonder if I have a Wi-Fi issue on this end. No, everybody else is still here. Just a second. For some reason, the mirroring stopped working, and I don't know why. I think I figured it out. This is wild. This was just working a minute ago. All right, I'm going to do my best I can without the diagram thing. But man, I really want that. This is important. I'm going to shut down the iPad and spin it back up again while I'm talking about this. Okay. All right, so we have this thing called a chip or a CPU, okay? And obviously it's meant to take some data in. We kind of looked at the fact that you can have these, connectors into the machine and data will come in. And by the way, that data just is a series of signals of 5 volts or 0 volts. That's all it is. We'll talk about like how to do that, but data is coming in and it's just electricity. And either at any split second, it's 5 volts or it's 0 or it's 0 and it's 5 volts and then it's 5 volts again, and then it's 0. It varies up and down, and that just represents data. We'll get into some details on that. But the data is coming into this actual physical chip that you see here on the left. That chip is a machine in its own right. It's designed to do work. And the people that create them at companies like Intel or AMD, Advanced Micro Devices, or Qualcomm, or now Apple, they make their own chips now. The people that make them, when they make them, design them to perform specific exact operations. And the operations they can perform are pretty simple, and given a little bit of investigation and thought, we could all determine what most of them are. They are things like do math operations. Take numbers and do some math with them. They are things like store some information in the memory of the computer. There are things like retrieve some information that's in the memory of the computer. There are things like take in data from an input device or send data to an output device. There's nothing very complex about any of those. It's just electricity on a wire. If it wants to read data in from a keyboard, for example, it'll literally pay attention to the wires that are coming in from the keyboard, and it'll see an exact pattern of 5 volts and 0 volts. And it goes, oh, that exact pattern, I have an internal list that's been programmed that represents the letter A. Good, I just took in the letter A. And then if it needs to send data on, like to a printer, and it needs to send something that looks like the letter T, it'll literally on the wire that will eventually connect back out of the computer and over to a printer, it'll send a series of on, off, whatever it is. It represents the letter T. And that'll arrive at the printer. It'll interpret it and go, oh, I need to make this symbol darker on a piece of paper. Nothing about this ends up being super complex. Again, the kinds of things that one of these chips can do are read in data from an external source, send data out to an external source, read data that's stored inside its memory devices in the computer, store or change data in a memory device in the computer, do some math operations, those kinds of things. They're not very complex things, are they? So when you're a company that makes chips, you'll build it to do all these things, and you'll document them. There's actually a manual that comes with it. And it says, hey, here's the available instructions for what this chip can do. There's usually only a couple dozen of them, because there's only so many things you can do at that fundamental level. And they involve all the things I just talked about. Dealing with the input-output devices, dealing with memory, dealing with math. It's not very much more than that. And all these instructions are literally built into that physical device. Now I'm about to add a little bit of complexity onto it, but I just want to stop. Are there any questions so far? Okay. Let's see if I can get this iPad spinning up in the background here. All right, so that set of instructions for the chip, it's got a really fancy name. It's called the instruction set. I'm being sarcastic. It's literally what it's called. The manufacturers of each different chip, they just publish this instruction set. It says, here's the things that this chip can do. What also is in that list is, here's a specific section of the chip to put the instruction you want it to do. These little areas on the chip are actual physical areas. If you had a microscope, you could look down inside it and find the actual physical location where you could input some data. And data, again, is just a pattern of ones and zeros. But you could find the place on the computer where you want to put that data. That particular place on that chip is called the instruction register. A register is just a place that will hold information. So there's this area on that little chip that'll hold what's the next thing I'm supposed to do. Why do I bring this up? Because you're going to write a lot of programs over the next several weeks and months and years. And no matter how complex they're going to look, ultimately, those programs need to get broken down into a series of instructions that can be fed into that chip. And they can only be instructions taken from that set of things it can do. That's all. Now, you can feed them in there very fast, and it can perform them very fast. But that chip can only do what the manufacturer said it can do. Any questions so far? Okay. Now, some of this stuff we're going to approach again from different points of view with different diagrams and words. You're going to hit it from a few different points of view. But that's one of the most fundamental things I wanted you to get is if we look at this physical picture of a computer, yes, we have electricity coming in and being dropped down to this 5-volt level that we're going to use all throughout the machine. But the important part here is that we have underneath this blue thing, and the blue thing is called a heat sink, by the way. It dissipates heat from the CPU. Underneath here is that CPU, and it's going to take data in that comes from these external devices, and it's going to work with it, and it's going to send it on to external devices. And when we say work with it, there's only a set number of things that it can do with the data. Along the way, the central processing unit makes use of some other things inside the computer that are valuable to it. It's got these little devices here where it can store information temporarily. That's called memory. It's got devices in it where it can permanently store information. Those are your disk drives. And it's got spots here that you can put other little boards that add some functionality to it. We'll talk about that later. But the important parts, there's only about 3 or 4 of them. We have electricity going through the machine. It's 5 volts. We can control its presence or its absence. We have information coming into this central processing unit and able to go out. And we have a sort of a storage area in memory where this central processing unit can put information it needs to work with. That's all a computer is. Any questions? Okay, now it's all verbal. I want to try to give you a little bit of diagram on it. So give me just a moment. I'm going to look at a power mirror, spin it up. Hmm. All right, I have a technical thing. Give me just a moment. I don't know why this is not behaving in a friendly manner. Yeah, this is really not being friendly. All right, we're gonna do some more work on this in the next class, and I apologize. This was pretty stable until it wasn't. Okay, so what I want to do now is I want to open this up because we covered a lot of ground here. I'm going to open it up to Q&A. I'll ask you a few questions. I want you to ask me anything you're thinking of. Okay, so we kind of started first just talking about what's the concept of a machine, something to do some sort of work that ends up helping people, and the idea of what compute means to figure out a problem, generally using numbers or determine the answer to something. What's the purpose of a computer? We covered this from a few different angles. What would you say the purpose of a computer is?
To take in data and then make a change to that data and then output it.
Good, excellent. Taking data, work with it, send it on. Good. What does that data look like? What form does it take inside the computer? How do we represent it?
Through the 5 volts, like the on and off.
Yeah, the presence or absence of electricity. Spot on, that's excellent. Okay, good. How do we get 5 volts into the computer?
Power supply.
Okay, good. What does the power supply do for us?
Reduce 240 or 120 volt into 5 volts.
Okay, good. Excellent. All right. I have this now. Let me share the screen. And I'll add a little bit of mass onto this. I want you to be able to see it. Okay. All right. So I've been going on and on about this central processing unit. Really? What did I do today? Wow. Okay. This is fun. I was really happy with this. %100 charged. There we go. Okay, good. Okay, so again, here's the computer, and inside is the power supply, and then down here is a central processing unit, and that's what we're going to talk about. I mentioned that on this big central processing unit would be a little area here where you could put in what's the instruction you want to perform next. Further, we talked about the fact that there's a set of instructions. Instruction 1, 2, 3, 4, 5, 6, and so on. There might be maybe 20 to 30 of these total for a typical central processing unit. And they are collectively known as what? What do I call these?
Instruction set?
Exactly. A publication often comes with these that you'll hardly ever see, where on one side it has the actual operation. I'm going to do this in a different color. In fact, I'm going to move down because we have plenty of room. So let's do this. You have the actual operation, and then you have a code for it. The operation might be something like add some numbers together, or it might be move some information into memory. But the code for it is the important part. It is a series of ones and zeros. Now, I'm just making up some ones and zeros there. That may not necessarily be the pattern, but here's what is important. This exact pattern represents this exact instruction right here. If you take that pattern and put it right inside this box here, what is that? 1 1 0 0 1 0 1 1. If you store that in there, and then you say to the CPU, hey, check what's inside this instruction register and do whatever it says in there. If it is this exact pattern that we find right down here, then it will take any numbers it was storing in special little locations and it'll add them up. Now, there's a lot of nerdy stuff that goes on under the hood about how they can make a machine, an electronic circuit that will do that. You don't need to know very much of it if you don't want to. It's enough to know that, again, the manufacturers created this instruction set. They said that this exact pattern right here represents adding numbers. I happen to want to add together some numbers that I'm storing in memory. The CPU knows about those numbers. The next thing I'm going to do is say, okay, please do the actual addition. Thank you very much. And so I will put in this exact series of ones and zeros into an actual physical location in that chip. And then I'll tell the CPU, do the next instruction. Thank you very much. And it'll look at that and it'll add it and it'll get whatever the answer is. So, and we'll expand on this in the next class. What this means is you might be writing something that says print 2 + 5, semicolon. That reads like English. Something will happen, this magic, they will turn it into a series of these instruction set instructions. In other words, a series of these ones and zero patterns. Now this something, anybody know what the term is for what happens there?
Process.
It is from a certain point of view, but that embraces a lot of types of things. There's a specific technical term for taking this English language-like instruction and turning it into these built-in instructions for the CPU. It's called compiling. That's what that verb is. These instructions are written in a language called machine language, because it's what the machine understands. And it isn't even that it understands it. Understands is in air quotes. It's that those are literally the only the only things it can do. They're the only things in the instruction set. So if we put in a series of instructions that match this instruction set and put them in one after the other in the correct spot in the CPU, it'll keep doing these things. It'll read information from the keyboard. It'll store it somewhere. It'll read the next piece of information from the keyboard. It'll store it somewhere. It'll see that we want to do an addition. It'll do the addition, store the answer somewhere. And that's what these little instructions written in this language called machine language tell it to do. Well, I don't know about you, but I don't want to write my programs as a series of these wonky patterns of ones and zeros taken from a book that describes the instruction set. I don't want to write programs that way. I don't want to write programs in this machine language. And I've done it, and it stinks. It takes a very long time. It's very error prone, and it's really hard to read your own code because it's just a bunch of ones and zeros. So instead, we don't use a machine language. We use what's called a higher generation language, like JavaScript or C# or Python or any one of thousands others. And then we have a special little computer program that does this. What's that computer program called? If the action it does is called compiling, what's the program called?
Compiler?
Yep. That's all a compiler is. It's probably a term you've heard before in relation to computers. It's just a special little program that on the one side knows, like Alexander was talking about, it knows the exact syntax for a specific language. And if it receives exactly properly formatted characters for that language, it can map that and send out a series of these machine language instructions that does what you want. And this is the way you can write programs in any one of thousands of different languages. And as long as someone built a compiler for it, they can map to the instruction set for that computer can run your program. If there is no compiler, you can't run that program. All right, that was a lot of data. While I've got the diagram up on the screen, any questions? Okay, cool.
Just one
Yes,
question.
please.
These ones and zeros, is there a limit to the number of ones and zeros?
Oh, that's really good. Yeah, and that's something we're going to expand on in the next session. But I will say this. We talked about this instruction register that I'm circling in red.
Mm-hmm.
I literally put 8 digits in there. In early computers, that instruction register could only hold 8 digits. But that was fine because when they built chips, those instructions, they only use 8 digits. So it was all fine. However, someone got really smart a little while later, and they built these chips so they could hold 16. They had another 8. You could put 2 instructions side by side. It would do one, and then it would do the other. Where we're at right now is that there are 1, 2, 3, 4 spots all in there. That is 64 digits. Did I do that right? No, there's 8 spots. Yeah. Wow, I need coffee. 64 divided by 8. Someone tell me, please.
8.
Yeah.
8. Thank you. Yeah, there's 8 of those spots. And by the way, this is getting ahead, a little teaser. We're going to learn all about binary next week. Each one of those little digits is called a binary digit or a bit. So early computers, they were 8-bit. The instructions can only take in 8 bits of instruction at a time. Then we have 16-bit computers, and then 32-bit computers, and now 64-bit computers. So the answer is yes, there's a limit. It increases as this technology advances. But at the end of the day, for the people that make the chips, they've only got like 20 or 30 different combinations. So they don't need very many digits to represent unique combinations. What increases is how many of them we can put in at a time and how much other information we can fit in next to the instruction. We'll talk about that later. Does that kind of answer that question for you, Sudesh?
Yes.
Good. That's a good question.
Yeah.
I don't want to leave you with any lingering confusions or stuff. Obviously, we've got a lot more to learn. But does anybody have any questions about what we went over tonight? Okay. So how many of you currently have your copy of You Are Not Stupid, the book that Jack Stanley and I wrote? Is there anyone who doesn't have a copy, digital or physical? You all have it, right? Okay, so you have 2 pieces of homework I'd like you to do before we meet next Saturday. And I'm going to write these down on the document that I've been using to go over all these items. And that way, and I'm going to send it all to you. Okay. Okay. Let me get the Zoom controls out of the way. So 1, I want you to describe the purpose of a computer and its basic operation as if to a bright 12-year-old in an essay. This is not some essay like you're in college. Just describe it in your own words, as if you're talking to a bright, about to be a teenager. That's all. I want it written down though. Okay, I want to see how you would explain this stuff to someone. This is a completely open book essay. You're free to review this entire recording. You're free to look up any resource you need to on the internet. You're free to email me and say, Eric, I got confused about something when I tried to write the essay. Can we pop onto a Zoom call for a minute? This is not some traditional academic thing where it's like, well, I didn't quite catch that in class. It'd be embarrassing or I'm not allowed to ask. No. If you're having trouble writing this down well, it's because I messed up somehow. So look it up as you need to, and then get a hold of me if you need to, and we'll meet and we'll talk about it and we'll work it out, okay? So that's the first part. And again, I'm going to give you a copy of all this. Describe the purpose of a computer and its basic operation as if to a bright 12-year-old in an essay. And the second thing is read as much of You Are Not Stupid as you can. That's all. Just as much as you can. I know we all have busy schedules. Okay. All right. Any questions? Okay, cool. One thing that I am really interested in is as we go through these first few classes, I really want your feedback on ways that we can improve the housekeeping, how we administer the training, anything I can do to make it better. I have taught this subject a lot, never done it quite like this. And so I know there's bound to be things where you're like, Eric, that didn't work as well as maybe you thought it would. I want to know about that. I have a very thick skin. So separately in the Discord, if you can just PM me and say, whatever your feedback is, I want to hear it. I won't be bothered. I'll appreciate you for letting me know. All right. Now, what I'm going to do right now is on the Discord channel, I'm just going to paste this stuff in. I'll make it a little more formal later, but I'm just going to go to the Discord channel right now and go to the group for us. And I'm pasting in all the notes I had, and it includes the homework. Oh, cool. I grabbed the links too. All right. I know we went a little over by 10 minutes. I appreciate it. I'll put out a note about the schedule change. From now on, they're all going to be at 8 o'clock Pacific. And you guys let me know if you need to increase the cadence of lessons, or if it gets too busy. I want feedback on everything. Anybody have any questions or comments before we end off? Okay, good. Good job. And again, there's going to be a lot of theory as we go through this. We'll be into coding soon enough, and you'll have your hands dirty, but you'll be doing all that work with a real solid understanding of what the heck these machines are all about. Have a great night. I will see you all Saturday evening or Sunday morning as the Sudesh goes.
Thank you.
Good night.
Thanks.
Bye all.
Bye.